Okay, so we are embarking on the last unit of this course, and there will obviously be a test. All right, we're down to, what do we got, 5 days this week, 4 days next week, 3.5 days the week after. All right. I think I might have just mentioned it, but I might as well show it right now for those of you who are interested in reviewing. If you go to our website and you go to worksheets, and the computer is, of course, painfully slow in the second period. It always is. Come on. Anyway. Sorry? Yeah, that's just me at the beginning when I was babbling on about various scientists and that, and I would say, gee, you don't need to know that. I put a page that it's not on the exam, but if you're interested in it, you could go and find more information about it. So then, there you go. There you have it. So this is obviously not coming up because it's second period and it always gets painfully slow. Look at there, due to network error. At the bottom of the worksheets page, there are, and I'll try to show you that at the end of class, there are a bunch of review packages for you to print off and start working through in preparation for the exam. We'll worry about that later. Okay, so Unit 4, Gases and Atmospheric Chemistry. To begin with, we have to talk about essentially what is a gas and what are the laws that govern gases. You all know of the state of gas and some of the properties of it. I'm going to go over some of them in a moment. But for this week, we're going to talk and we're going to do a few little experiments on the actual ways in which gases behave in terms of their properties. What happens when you compress them? What happens if you cool them off? What happens if you add more gas? What if you add some gas to a balloon? So what we need to do is we need to determine the rules that affect gases. All right. Historically, gases are essentially where chemistry began. It was really the study of gases that really kind of got things going quantitatively. Scientists were creating gases, testing gases, and they were also studying things like pressures and temperatures and measuring gases. So for this week, we will be talking about the rules of gases and how they behave and how we can calculate things using them. In the second week, we will be talking about then chemistry involved in gases and how we can do stoichiometry with gases, how we can take a certain amount of gas and do some mathematics and figure out how many moles of gases there are. So this week, we're talking about the rules of gases. And to start with, we're going to talk about properties. And if you had done your reading, you wouldn't have to write any of this down because it should be all in your, it should all be in that reading thing, right? Because I asked you to define the properties of gases. So it should be all there. And if you haven't done your reading, then shame on you, and you're all writing feverishly. And I can see not every one of you, many of you, writing down all this stuff. So before we talk about gases, let's go over and talk a little bit about the other states of matter. Solids, we define a solid as having a definite shape and volume. All right. In other words, you put it in a container and they just sit there. They don't do anything. They don't change their shape. They don't change a volume. They just kind of sit in their spot. They're incompressible virtually. You can't really squeeze them. And they definitely don't flow, and there's a little animation showing a chunk of solid in a beaker. You move it back and forth, and it slides across the bottom, and the particles are not able to flow past each other. All right? Again, empirical means with our senses what we observe, etc., etc. In terms of liquids, empirical properties of liquids. If you don't get this all down, like I said, you should have read it anyway. And if you don't, you can always go back and check it online and finish it off. They assume the shape of the container. You pour some liquid into a beaker, and that liquid flows to the bottom of the beaker, and it takes the shape of whatever is you've poured it in. It has a definite volume, which means you pour it into the beaker, and that amount in which it occupies, that space in which it occupies, is constant. All right? So you put 50 milliliters in the beaker, it's still 50 milliliters if you pour it into another container. It is virtually incompressible. If I were to take a syringe and put some water into it, I cannot readily squeeze that because the water takes up so much of the space and I can't squeeze it into a smaller space. So I cannot compress a liquid and it readily flows. And that's a comment on the particles where they're able to move past each other as you slosh that container around. And so you can pour it, it moves. If you move the container, it readily flows. Talking about gases, and I don't have an animation for this one, but a gas assumes the shape and volume of the container. So it doesn't matter how much of a gas you put into a space, that gas will automatically fill the entire space. All right? So if I were to take, even though there's even air in the room already, even though there's a gas in the room already, if I were to take this propane cylinder and I were to let some propane out, okay, I've let some propane out, that propane is not going to just sit here in front of us in the room. It's going to spread out, and it's going to ultimately fill the entire room. Even though there's already air particles there, there's so much space between those air particles that that propane is going to be able to fill into all corners of the room and kind of spread itself out evenly and take up that shape. Whatever the shape of the room is, it's easily, it fills it easily and it assumes the shape of the container. It doesn't matter what gas there is. They all kind of spread out so they're nice, evenly distributed. Highly compressible. I can easily compress a gas if I take the syringe, if I draw some air in. I got to find the open valve way. So if I draw some air in and I close it, nope, that's just pushing it out the other way. Oh, no, there we go. I can easily compress a gas, all right? I can squeeze that down to a smaller volume. I can actually draw it out to a larger volume. The plunger will end up going back to where I started. The volume that I initially put in there. And so it's easily compressible and it readily flows. Gases flow from one area to another. If we were to, wind is a good example of that. If you've got a high pressure system in one location and a low pressure system atmospherically in another position, then that air will flow automatically from high to low pressure. Okay, so what we want to talk about is, what is it about gases that makes them have all of these interesting properties? And in order to make sense of that, we need to review the kinetic molecular theory. And the kinetic molecular theory is one of those theories that we teach you probably back in grade like 7. I know my daughter's in grade 7 right now. She was doing a little bit on the kinetic molecular theory. You see it again in grade 9. We mentioned it at the beginning of this course. I can't even remember what we were talking about. Why did we talk? Oh, we probably talked about when we were talking about atomic theory, right? A little bit of the kinetic molecular theory. And now we're getting you to write it down again. It's one of those ideas of how matter behaves, but it's very simple and it's very useful. Matter is made up of tiny particles. Back when this idea was proposed, it was soon after Dalton proposed the existence of atoms. They weren't sure what the particles were, but it didn't matter. They were very confident that it was made up of tiny particles. And they're in constant motion. It took a long time for scientists to really believe such an idea. Some scientists, even in the early 1800s, still believed that matter was not made up of little particles, but was continuous. That's an idea that Aristotle had way back when we were talking about atoms and Democritus, right? I would have mentioned Aristotle. Aristotle believed that all matter was continuous. You could cut forever. Remember this story about the cutting? You could cut. You could take a piece of material, keep cutting it, make it smaller, get a smaller knife, and you'd never get to the end of being able to cut that piece in half. Democritus believed that you couldn't do such a thing. This idea of particles goes right to the heart of what Democritus was saying. Again, in the early 1800s is when Dalton was saying, okay, atoms exist, at least we think they do. We can explain how gases dissolve in liquids that way. And then this idea of, okay, if there's lots of particles, then how are these particles behaving? And it has everything to do with their motion and the force of attraction. Like I said, many chemists didn't buy it. They were still thinking, no, I'm not sure about these particles. It wasn't until Albert Einstein in like 1905 explained something that's called Brownian motion that scientists said, hey, you know, I think maybe there's something to this particle thing, which is quite sad, 1905. And they're just starting to buy the fact that, hey, oh, maybe they are made up of little particles. Brownian motion is an interesting effect. When you look at smoke in a microscope, if you were to look at smoke, whether it's cigarette smoke or smoke from a fire, it doesn't make any difference, smoke. If you look at it in a microscope, you can see the individual particles that make up the smoke, all right? And if you watch it, they dance around. In a microscope, you can actually see the smoke particles wiggling and jiggling in place. They kind of wiggle. They don't move around a whole lot. They'll move around if there's gravity. It'll move if there's air currents causing them to move. But if you have a nice sealed container, the smoke in there just wiggles and jiggles. And the scientist by the name of Brown discovered this, I think in the 1800s. No one understood what the heck was going on. Albert Einstein did some calculations. If we assume that there are particles in the air that we can't see the air particles. This is a transparent solution. If we assume that the particles in the air, and I'll just make them a different color, blue, and those particles have mass, and those particles are in constant motion, then sometimes those air particles will bump up against the smoke particles and give them a bump and cause that particle to move. Einstein did calculations on the masses of the gas particles, assuming that they existed, and on the mass of the smoke particles, and if you had so many collisions per second, how would that particle move? And he explained Brownian motion, the observed motion, with the theory of the fact that there were little particles. No one else had done it before. Big check mark on that. We've got some evidence that this is little particles moving, okay? All matter is made up of particles and they're in constant motion. If an object gains heat, its particles have more kinetic energy. That's why it's called the kinetic molecular theory. Remember, kinetic energy is the energy of motion. Anything that moves has kinetic energy, even gas particles, or particles in a solid or particles in a liquid. The hotter something is, the faster the particles move. That makes good sense. Energy is transferred from one part of an object to another by means of collisions. So if we have the heating of a metal spoon or even a scoopula, I got a scoopula in my pocket, and if I were to put that at one end of it in a Bunsen burner, the other end would eventually get hot, right? We call that conduction of heat. We now know that that's the particles in the metal starting to vibrate. They collide with adjacent particles. They vibrate, which collides with adjacent particles, etc., 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 and the heat is transferred along the line, okay? So, faster moving particles is heat. Faster moving particles collide with other particles and transfer their heat. Types of particle motion. This again was in the reading, which is what we wanted you to do. So now we're probably going into more detail than you've probably ever learned in terms of kinetic and molecular theory. But scientists have sat down and thought very closely about how particles can move. What type of movement is allowed when it comes to molecules and atoms and other types of particles? There are essentially three types of motion that a substance, that any object can have. This is not true just for gas particles or solid particles or liquid particles or molecular particles. This is true for anything. Any object, if you think about it, can only have these three types of motion. Translational motion, straight line movement. If you've taken mathematics and you've done things like changing the shape of a side, I don't remember what it's called. My wife teaches math and they do this in grade 9. What do they call it when you take an object and you make it bigger or smaller, or you rotate it, or you move it on a grid? Transformations. I don't know. You guys do these transformations? And do you call it, when you move it from one place to another, a translation? Do they still call it? So that's what we mean by translational motion. That you move from one place to another. That's not a big deal. So if you've got a molecule and it's here and it moves to there, we say it's a translation. Straight line motion. That's not a big deal. Most of the motion we encounter is translational, right? You walk down the hall, you're translating down the hall, right? You're moving in a particular direction. Same within your car. You get in the car, go down the road, you're just going straight. Rotational. That's obvious. Any object can rotate as well. I think also in your transformations unit, you might have done rotations around a point, right? And so that's the same type thing. You want to avoid rotational motion in your car. That wouldn't be a pleasant experience. If you're going down the hall, I suppose you could do rotational motion. You'd look a little goofy. Maybe at a dance, you want to do rotational motion, right? No? Rotational motion? No? I don't know. It's rotational motion. Atoms can rotate. Molecules can obviously rotate. Vibrational motion. Now, vibrational motion does not necessarily take place in all objects. If you're talking about a simple atom, like just one atom, it really can't vibrate. It can rotate and it can translate, but it can't really vibrate. I guess it can vibrate like this. I guess it can vibrate in a solid. If it's in a solid, it can move back and forth. The reason I guess it moves back and forth if it's a single atom is because it's being encountered by other atoms. There's some kind of bond there. If you want a vibration to take place in a molecule, there has to be a bond of some sort. If we're talking about a solid, maybe like a bunch of iron atoms in a piece of steel, all right? All of these iron atoms are packed together, and they're actually feeling the presence of each other. They're actually being attracted to each other a little bit. So when they vibrate back and forth, then they're actually responding to the forces that are being applied by adjacent atoms. In a gas, a single atom can't vibrate. It can go off in straight line motion. It can be rotating, but it can't really vibrate because there's nothing to vibrate up against. If we have larger, more complex molecules, like carbon dioxide, all right? Carbon dioxide has bonds within them, which means this carbon dioxide can travel in a straight line, all right? It can rotate, all right? And it can also vibrate. Each of these atoms can vibrate with respect to each other. I think we all know that carbon dioxide is what we call a greenhouse gas. I would hope we're all aware of that. A greenhouse gas is a gas that's in our atmosphere that has the ability to catch heat coming from the earth and trap it and then re-radiate it back down to the ground. That's why our earth is warm and habitable. Because if we didn't have greenhouse gases in our atmosphere, all of the heat that came into the earth that would come from the sun, the ground would get hot, kind of like a piece of steel on a hot sunny day, right? You touch that steel, whoa, that's really hot. That's from the energy coming from the sun and heating it up. Then it re-radiates it as heat energy. and that heat energy tries to go back into space. If we didn't have an atmosphere, all of that heat energy would re-radiate back into space, and the air would be cold. The ground would be hot, but there would be no air if we didn't have any atmosphere. So then it would be like the surface of the planet would be hot, but this high off the ground would be unbearingly cold. We wouldn't survive. Greenhouse gases are important things. So what do greenhouse gases do? How do they trap the air? It has everything to do with this vibrational motion. If you put something like oxygen in the air, that's good stuff, because we breathe it. We need oxygen in order to survive. But oxygen can't really vibrate. It can really vibrate in one way. It can have the oxygens come together and then spread apart. In other words, the oxygen atoms can do a little bit of that. That's about the most that an oxygen molecule, can do in terms of a vibration. But as soon as you add a third atom, you have all kinds of different vibrations. Now I'm going to go out on a limb and risk being ridiculed, but as a teacher, I can handle it. If my head is the carbon atom and my fists are the oxygen atoms, there are many different ways in which it can vibrate. It can do this. It can do this. It can do this. Many, many different ways of vibrating. Each one of those different vibrations is another way for the molecule to absorb heat. The more possible vibrations a molecule in the air can do, the more heat it catches, and the better it is at being a greenhouse gas. Actually, I did a stationary carbon dioxide molecule. If I were to put together all three of the possible motions of carbon dioxide, it could be interesting. I hate going to dances. I hate it. I hate dancing. I'm not a good dancer. In university, we would go to the pub and we would go to they'd all be out dancing. I wouldn't do it. But if I'd known this, I could have pulled off the dancing. Here's what a carbon dioxide might look like if you put all of the motion together. So I'm going to do some translation, some rotation, and a little bit of carbon dioxide vibrating. So here we go. This is what it would look like. I would have been a great dancer out there if I had to put it in a context of chemistry. Oh well. Maybe I should go to a dance sometime. I could do my best carbon dioxide. It's cool. So depending on how they move, determines on how much energy they can absorb. Because remember, heat is the motion of particles. And the more ways in which a particle can move, the better it is at absorbing heat. That's what makes carbon dioxide such a good greenhouse gas. The problem is if we put all kinds of carbon dioxide into the atmosphere, we're going to catch more and more of the heat, and then the Earth is going to heat up, and then, well, you've all heard the stories. I'm not here to talk to you about a debate on greenhouse gases, but this is why greenhouse gases absorb the energy the way they do. I already sent it up, Jamie. There are many other molecules in the atmosphere that are better at being greenhouse gases than carbon dioxide. If three atoms you think vibrates like crazy, try something like methane, which is natural gas. That's methane. Methane's also produced in the stomach of cows and then released from the stomach of cows. Yes, exactly what you're thinking. Hey, if you would like to study those gases produced by cows, the University of Guelph has designed a device that they strap to the back end of a cow so they can catch all the methane produced by cows. That's what you do at Guelph, which is why I went to Western. But that's a concern as well. There's a lot of cows in this world, and they're producing a lot of methane. And that methane molecule in the air vibrates in many different ways. That is also a very strong greenhouse gas. Methane is also produced by decomposing organic matter like in a swamp, all right? If you saw if you've been in Mr. Edgar's room where they make those little, all that disgusting stuff in a jar, that's producing methane. All he does is grind up like food waste, add some water, add a little bit of dirt, which has some bacteria in it, and give it a day or two and a little bit of heat, and it's producing methane. All kinds of it. All right. Some people want to take that methane that's coming off of all these manure pits and piles and garbage dumps and turn it into good energy. Actually, here at Petrolia, they've got a generator that's running off of the methane that's produced at the Petrolia garbage dump. That's that big building that's right close to the road there, and it's got an engine that runs in it all the time. It's always screaming away because it's running off of the methane gas. It's a generator. It's running a generator. So the gas that's coming off of the garbage is being collected in pipes. It runs a motor, and then it's running an electrical generator, which then just feeds electricity into the electrical grid. Oh. Yeah, so they're generating electricity from that gas. All right, but those are greenhouse gases too. Okay, so this little discussion was really just about the three ways in which particles can move and how we can store energy in it. You don't have to worry about the greenhouse gas thing. That's just me giving you a little bit of information that there are all kinds of different greenhouse gases. Water vapor is a great greenhouse gas, right? If the air is humid and there's a lot of clouds around, then when the heat comes in, it's trapped by that humid air and re-radiated back to the ground. You probably are aware that if it's a very clear night and it's cool, there's a chance of frost. That's because there's no water vapor in there. It's a very dry air. There's no clouds, and the heat leaves very easily. You put some clouds and some water vapor in the air, and you don't have the probability of frost because it's also a greenhouse gas. All right. Now water vapor is not a problem in the atmosphere because when there's a lot of water vapor in the atmosphere, it rains out of the atmosphere. Right. If the air gets too humid, then it just rains it out, and rain falls. Too bad carbon dioxide couldn't just rain out of the air. Then we wouldn't have a problem, but it doesn't, because it doesn't get to a point where it can rain out of the air. It doesn't ever get to a point where it's liquid or solid. Okay. All right. So that's just a little aside there. Let's keep going talking about our particles. So we now want to talk a little bit about the way order comes into play when it comes to the states of matter. This is a little introduction to a concept you'll learn next year called entropy, but it's not a big deal. We won't bother with it right now. Just we want to talk about the way particles exist in solids. They're highly ordered. In other words, they're sitting in nice little rows and crystals. They have very little translational motion. Vibrational motion is really what dominates in a solid. In a liquid, you've got a combination of a little bit of translational. They're able to move past each other, but they're not able to move free out of the liquid. So you got a glass of water. Those particles are moving around. They're moving around within the liquid. You put some ions in there, they're moving around as well. Which means it does undergo rotational, vibrational, and translational. We'll put that in the middle. And then gases, they're the most disordered. When I teach you next year, and I'll bring it up right now, I always think of an analogy of teaching when I think of the order, right? The analogy of a solid in terms of teaching and order is like the classroom. I'm a fan of order. You guys would represent a solid right now. You're all sitting nicely in your grid, not doing much. Arms vibrating a little bit if you're writing something down. Vibrational motion. That's good. I like order. Liquid. I guess the student analogy of a liquid would be like a phys ed class. I don't know if I could handle being a phys ed teacher. A little too much disorder for me. Okay, we're going to play, I don't know. Dodgeball. Dodgeball. I was going to say something about a rubber chicken, because I know that phys ed people play with rubber chickens for some reason.
What's that game? Chicken.
I don't know. There's all kinds of chicken games you guys do. Games of low organization or something.
It takes a lot of skill.
Can you imagine an entire unit? Games of low organization. Anyway. To me, that would be a liquid. Okay, there you go. There's some dodgeballs. Go ahead. Just don't kill each other. Then there would be people, kind of bouncing around and getting hit by balls and running away and that type of thing. But you'd be contained in the gymnasium, right? That's why I think of it as a liquid. Phys ed would be contained in the gymnasium. A gas, kindergarten teacher. You kidding me? Total chaos, constantly. Try to take them in the yard for something. As soon as you open that door, they would fill the entire playground right into every corner. And if there was a little opening in the gate, they would get out of that container. And they would be just wherever. It would be total chaos. Oh yeah, I don't know how to do it. My sister, she teaches kindergarten. Insanity. So in terms of analogy, my class, nice and order, and I thank you. Phys ed, kindergarten, chaos, everywhere. Give them some space, they're gone. Okay. We're not going to look at that. Okay, now let's talk a little bit about temperature. So now that we've talked about the way we can imagine gases, because that's really what it's all about, in our minds being able to think about what the particles are doing and how they're behaving. And now that I've described to you as gases as being absolute chaos, particles going everywhere, rotating, vibrating, translating, all kinds of motion. We're now ready to talk about some very important properties when it comes to gases. It turns out chemists, physicists have discovered that there are 4 numbers that you need to write down to perfectly define a gas. And actually, it's not just a gas, it's any substance, solid, liquid, or gas. But we're only going to look at it in terms of gases. You're all writing very intently, so I will let you. So as I was saying, scientists have determined that there are 4 numbers that anyone needs, that the universe seems to need, in order to define a substance, solid, liquid, or gas, but we're going to primarily concern ourselves with gases. The first one, we've already encountered it, and I didn't really talk much about it, and that's because it's not that exciting, and the first one is volume. You don't have to write this down. We'll be writing it all down later. But we need to know how much of a substance. It's volume, all right? And that's something that's fairly easily measurable. If it's a liquid, we put it in a graduated cylinder or maybe even a burette. If it's a solid, we can measure its dimensions or put it in some water and have it displace some water. We can measure the water. So volume is the number of milliliters, the space it occupies. The second thing is the temperature. What temperature is that substance at? Because a piece of ice that's at -4 is going to have actually quite different properties than a piece of ice that's at 0 and on the verge of melting. Okay, so temperature also is a very important defining factor of a substance, and that's why I'm going to talk about it here for a moment. I'm going to just keep going on this list. The third thing is pressure, all right? What kind of pressure is that substance under? Is it out in the vacuum of space, or is it here on Earth just at kind of regular pressure? Or is it buried under the ground under huge pressures, right? And we hopefully have an idea that in different situations, things are going to behave differently, right? Materials do behave completely differently in the low pressure of outer space, or even just space at the space station, than they do here on Earth, right? So pressure, very important as well. And the last thing that defines any substance, but we're primarily worried about gases, is the amount of the stuff we have. I put an N there. That stands for number of moles, right? So how much stuff are we talking about? Are we talking about a lot of stuff or just a little bit of stuff? The number of moles along with the volume can eventually get us the density, right? Because we could figure out the mass and the volume. So things like density are built into these four numbers. So that's why we need to know very much about them. Volume's easy to understand. We've all measured volume. Number of moles, I think we're getting the idea of that. It's the number of particles that we're dealing with. So it's temperature and pressure that we've got to really kind of master right now so that we can continue on and understand what's going on. So what do we mean by temperature? A temperature is a measure of the average kinetic energy of the particles in a substance. We know that all the particles in a substance move. And that's the translational, rotational, and vibrational. If we could add up all that energy, all those movements, and then we could add up all of the movements of each of the individual particles, and then if we divided it by the number of particles, we could get an average. Now, there's no way for us to actually do this. The reason we know that this is truly an average comes from some mathematical, computational stuff done by a guy by the name of Maxwell and his buddy by the name of Boltzmann. Doesn't matter. It was done in the mid-1800s, and they did a whole bunch of math to try to figure out the way this kinetic molecular theory would work if we started to add up all of the energies of the particles. And it works very well as a theory. So we know that the temperature is a measure of the average kinetic energy. If something's hot, then there's a lot of kinetic energy in the particles. They're moving fast. If something's cool, then there's not much kinetic energy in the particles, and they're moving slow. Here's my really exciting animation here. Ooh, did you see? When I clicked cool, they slowed down. Fast, slow. All right. Because it's a kinetic energy, it's not as simple as fast and slow. Heavy particles will automatically move slower, and lighter particles will automatically be moving faster. And that's because heavy particles carry more kinetic energy. Okay, it's that simple. If you want to understand why examples of heavier particles carrying more kinetic energy, if you have somebody on a pedal bike, you're walking down the street, and you're walking on the sidewalk, and the pedal bike comes on the street, and the guy on the pedal bike that doesn't have a lot of mass runs into you, boom, you fall down, you're like, hey, what are you doing, man? Nobody's really hurt. But if you were to step out on the street and get hit by a heavier object like a car, then obviously more damage is going to be done. They could be going at the same speed, but the heavier object automatically carries more kinetic energy, okay? So at a particular temperature, if they've got the same kinetic energy, heavy guys move slow, and the lighter guys are moving fast, okay? It's also an average. It's not like the particles in a gas are on a highway. On a highway, everybody's kind of going the same speed. I guess you could have some fast and slow movers. But in a gas, the particles, and all substances, all types of matter, the particles have varying speeds. Some are going slow, some are going really fast, but most of them are in the middle. And so we've got this average, okay? So we've got slow movers and fast movers, and then we've got some that are in the middle. Okay, temperature is related to the speed. There's a little note about, and I got to bring up one more thing here. There's a little note about thermometers and how we measure things. I'm going to get Nathan going on his test here. I'll get to the periodic table. You need your calculator. Just one change here for a minute. Yep. We'll get rid of revised. Don't mind that word revised there. These, do them on there, and then still fill in on the thing. Okay? Oh, can you do that? Just pick a desk mat there. We use a thermometer to measure temperature. Again, that's one of those things you've used over and over again. It's something that I really don't need to show you how to use. You may have talked about how it works as well. I'll go over that in a moment. Hopefully you have in the past. What I want to talk about just before I get into how it works, and that's in the top bullets, is just my little representation of some important temperatures. 0 degrees Celsius, freezing point of water, right? 100 degrees Celsius, boiling point of water. Two very important temperatures. That's how our Celsius temperature scale was kind of invented. Actually, it was first called the centigrade, with centi being 100. And whoever designed the centigrade scale, and I can't remember who it wasn't Mr. Celsius. That came a little later. But anyway, 0, put it in some freezing water. You can define 0 on maybe an uncalibrated thermometer. Put it in some boiling water, define 100. Take a ruler, break it into 100 individual little units that are evenly spaced, and you've created yourself a Celsius thermometer, okay? Now, other important temperatures. Way down here, negative 273. What's this also known as? Any ideas? Anybody learned this from a previous class? This is the coldest possible temperature that can exist. Yep, what do you got, right? Or Ben? Yeah, it's called absolute zero. Absolute zero. And I'm going to talk about that just in a moment. It turns out that nothing can get colder than minus 273 degrees Celsius. And I'll mention why in terms of the particles in a moment. The chemist that kind of determined this, his last name was Thompson, but he was an English scientist and was knighted, or whatever they call it. He ended up getting the knighted Lord Kelvin from a location in England, Kelvin. And so because his title was Lord Kelvin, this is called the Kelvin scale. The Kelvin scale has exactly the same size, degree units as the Celsius scale, except the only difference is that it starts down at the very bottom, or the coldest possible temperature. Because it made good sense to, if you had a coldest possible temperature, why not define that as 0, the starting point of temperature? And so 0 Kelvin is negative 273 degrees Celsius, which makes then our 0 degrees Celsius 273 degrees hotter than that, and therefore it's at 273 Kelvin. And the boiling point of water then is at 373 Kelvin. We're going to be using the Kelvin scale quite a bit. There's a very simple, easy way to convert. If you have the Celsius temperature, just add the 273 degrees, and you'll turn it into the Kelvin temperature. Yep. Oh, that's an interesting question. I don't have the complete answer to that, but I'll give you my best answer. On this thermometer here, there is a Fahrenheit scale as well, right? You can see here that it's got Fahrenheit on this side and then the centigrade on this side. And the 0 for the Fahrenheit scale, you'll notice, is down here at about minus, I don't even know it. I don't use the Fahrenheit scale very often. Minus, it's looking like almost minus 18, okay, degrees Celsius. I do know, and I read this somewhere, but I don't know the rest of the details, that in the laboratory, if you add salt to an ice water mixture its temperature actually goes below the freezing point. If you've ever made ice cream, or if you've ever seen anybody make ice cream, you use salt and water on the outside. And that actually causes the temperature to decline, okay? When you go on into university chemistry, you'll learn something called colligative properties, and you'll do calculations to figure out exactly how cold it can get depending on the amount of salt you put in water. We used to do it in the grade 12, but they don't do it anymore. The lowest possible temperature that you can achieve with a salt-water mixture is about minus 18. So what Fahrenheit did was he had 0 be the lowest possible temperature that he could achieve in a laboratory by mixing salt with water. So he decided that's a good place to start. I don't know how the size of the degrees were decided on. Something obviously significant must have been up here for his second point, and then he divided it by equal numbers. But I know that that's where he started his, and that's why his is down in here. But it turned out that Celsius was a much easier way of looking at things, so we've adopted this one. Okay, so that's one a little bit of a reason on why he started there. Just some weird things about temperature before I talk about how it works. Have you ever noticed how if you're talking about the air, right, we all talk in Celsius, right? So how hot's it going to be today? It's only going to be 15. Bring your jacket. Okay, right? Oh, it's going to be 22. Okay, I don't need my jacket. Oh, it's going to be 32. Oh, it's going to be sweltering hot. But if you're talking about water, especially in Canada here, for some reason we're stuck between two unit systems, right? In the United States, they talk about Fahrenheit. Doesn't matter what. But in Canada, we talk about Celsius when we talk about the air. But if you're talking about water, you never talk about Celsius. Hey, come on over for a swim. The pool is great. Really, what's the temperature? It's 18 degrees Celsius. And you go, what? Do I want to swim in water that's 18 degrees Celsius? I don't know if I want to swim in that water. But if they said, it's 82 degrees. Oh, yeah, that's fabulous. I'll go for a swim in 82 degrees. Why is that? It's bizarre, don't you think? Two completely different unit systems to describe air and water, and we cannot make them mix together. Our brains, we're strange people, Canadians. It's got to be the only place in the world that does that. But for some reason, we use Fahrenheit for a swimming pool, and we use Celsius for the air, and we can't make our brains go back and forth. It's probably why we feel so cold when we get out of the pool. It has nothing to do with that, but we could say that it does. Oh man, I was just in 82 degree water. Now it's 20 degree air. No wonder I'm freezing. That's wrong, by the way. I'm glad you're giggling at that. How does a thermometer work? How does a thermometer work? How does this thing work anyway? Gee. How does a thermometer work? Okay, so remember, all the particles are bouncing around and moving around. And the air particles are bouncing off of this bulb. It's actually bouncing off of everything here. But this bulb contains a reservoir of some alcohol, all right? There's old mercury thermometers. You see them with the metal in there, the shiny metal. We don't use those anymore because if you break them, you got mercury in the air, and mercury's bad. So what happens? The particles strike this, and they strike the glass, and the glass particles start to vibrate. Then the glass particles vibrate up against the alcohol particles, which is a liquid. And what does that do? That kind of causes everything to kind of bounce up against each other and bubble up. I'm trying to think of an example of what I'm talking about. You know, you're not going to be able to think it. There used to be a Fisher-Price toy. It's got to be 1 million years old. That has the wheels and the popper in it. Pop up, pop up, pop up, pop up, pop up, pop up. You know what I'm talking about? And all the balls go, yeah, that type of thing, right? Okay. So you can imagine that's exactly what's happening in a thermometer. Right now, the heated air particles are bumping up against the alcohol particles. And so what are they doing? They're all bumping up against each other. Now gravity's trying to pull those particles back down into a nice little pile, just like in the popping machine. But because there's always these other particles bumping up against it, it causes those particles to bump, 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 and then it gets to a certain height. If it gets hotter, it means there's more bumping going on, and it bumps to the top. If you could take your Magic School Bus, and you could, is Magic School Bus so old that nobody knows Magic School Bus anymore? Oh, okay, good. I'm getting pretty old here. You know, Magic School Bus was quite a while ago. So if you could get into your magic school bus and you could zoom in to the surface of that alcohol, even though it looks like a nice line here, it would be a chaotic, there would be particles bouncing around and trying to get out and then falling back in, and it would be a chaotic surface, just like the inside of the popping machine. If you could build a big enough popping machine, the Fisher-Price popping machine is what I'm going to call it. Let's say you could build it with a big cylinder above it, and you put more balls in it. If you went slow, the balls would just kind of pop up a little bit, be like cool, cold. But if you ran fast with that machine going, right, you can imagine, pop, 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 it's popping like crazy, all those little balls would rise up to a higher spot. You could put a mark on there, and you could probably translate that into the speed of your running, right? It would be like your speed. But in this case, it's the kinetic energy of the particles that are around it. If we bring this outside where it's cool, there's less energy going to that. It settles down and goes to a lower temperature. That's the way a thermometer works, all right? There's some chaos going on in this little thermometer. Chris is formulating a question.
So like the measurement of degrees Celsius, does it have anything to do with like velocity?
Of what?
Yeah.
Of what?
Velocity of particles.
Yes, it does.
Okay.
It's directly related to that. The velocity of the particles is translated then into the kinetic energy of the particles, all right? And through an equation, we could get the temperature. But you're right. At a fundamental level here, the speed of the particles heading these guys determines how high that is. It's that simple. Yes. Yep. Okay? All right. So that's how a thermometer works. And we've introduced you to some important temperature units. We're not going to look at that. Okay, so let's finish off by talking about a couple of little definitions here, just to complete this. So actually, as I read this, I misspoke a little bit with the thermometer, and when you're done writing, I'll explain how I kind of misspoke a little bit. And it's a good illustration of what we mean here by the condensed state versus the gas state. We've talked about intermolecular forces. They're the forces that hold adjacent molecules together. They don't hold the molecules together. That's intra. But inter is what holds adjacent molecules together. Right now, in this alcohol that's in this thermometer, there are actually some hydrogen bonding going on, and that's what keeps this a liquid. Okay? A moment ago, when I was describing it to the way this thermometer works, I said gravity pulls the particles back down. It does in the popper. That's what keeps the particles from flying out of the popper, gravity. But in a liquid, and when we're dealing with the mass of little molecules, gravity is a very small effect. There's not a lot of gravity holding a molecule down. What keeps this in the liquid state is intermolecular forces. The hydrogen bonding that exists between the alcohol molecules, as the thing is trying to pop them up and push them up and expand them, they're being held back down by hydrogen bonding. An alcohol molecule tries to escape, and then it's being held back down by hydrogen bond. Okay? So intermolecular forces is what keeps things condensed. If you were following Chris Hadfield movies and various things, you saw him with water, right? They all like to do the water thing, hanging out there, that thing of water. If it was gravity that was holding liquids together, then that water should have just, right? Should have just turned into a gas. But it's not gravity that holds liquids together. It's their intermolecular forces. So the hydrogen bonding in that water kept it together in a sphere because there was no gravity to hold them there. So intermolecular forces hold these things together. If the intermolecular forces are weak and they're not strong enough, in other words, if the particles are not sticky enough to hold together, then they're able to fly away in all directions. And then we've got a gas. So when something has low intermolecular forces, they're able to get away from each other. They're able to fly apart from each other. And they exist then as a gas. If they've got high intermolecular forces, they'll be sticky to each other, and they will exist as a solid or a liquid. We can cause a solid or a liquid to vaporize and become a gas by giving the particles so much energy that they can't hold themselves together. They're bouncing off of each other so hard that, boom, they go off and become a gas, like when you boil water. When you boil water, you've put so much kinetic energy into the particles that they bounce off of each other and take off into the gas state, and away they go. All right? Okay. I'm not going to show that movie. Nope. There's the homework. That was for when I was absent one time. That was for a supply teacher. I am going to continue on and talk about pressure for the last 15 minutes or so. I might not get finished, but I now want to talk about pressure. Are those the same as on the reading thing? So if you've done it, you're in good shape. For the rest of you, you got work to do. Okay. What is that? It kind of is, but we're just talking about the next property, right? So you can continue on if you'd like. It's still talking about particles and movement and all that stuff. So if you'd like, you could, or it could follow under temperature as being the next thing that we're talking about. However you would like to deal with that, that's up to you. So we've dealt with volume because there's not much to deal with. Milliliters, liters, we know how to measure it if we had to. We know how to talk about the units. We know how to convert the units. Temperature, I've just introduced you to it. You knew about temperature. I may have introduced to you the Kelvin scale and the fact that there's a lowest possible temperature, and we'll deal with that in another day or two. And we've definitely encountered moles, right? We've been talking about moles for quite some time. So the last thing we really have to talk about is pressure. And what is pressure, and how we measure it, and how we convert it, et cetera, et cetera. Pressure is a physical quantity. Temperature is a physical quantity. All of these things are physical quantities. All of these things do not affect the chemistry of a substance. All of these variables we've talked about, like I said, are required to define a substance so that we can say we know all the important information about that substance. So pressure is a physical quantity. It's a physics thing. I do have an equation. There is an equation for it. I don't know if I put it down here. No, don't write that down. Let's put the equation down. I'll write it on the board. Actually, no, I'll write it on the thingamajigger. It's the amount of force applied per unit area. Pressure, P, is equal to force divided by the area. There you have it right there. It's that simple. If we do a little unit analysis, what do I measure force with? What is my unit for force? And I'm recording this so Mr. Petrus can hear the lack of answers. Yep, it's a Newton. Area measured in, any ideas? It's a square something, right? Square centimeter. Let's do meter squared. Meter squared. A Newton per meter squared is a pressure. Now, like many other units in physics, we've often given the complex unit a different name to honor someone and to make it a little simpler. The person that we've named this unit after, his name is Pascal, so it's a P-A, capital P-A, a Pascal, all right? So what's 1 Pascal? 1 P-A is equal to 1 Newton, all right, spread over 1 meter squared. Now that's not a lot of pressure. If I were to get out some apparatus here, what have I got here? That is 200. I wish I had a 100. We got a 100 here. That is 200 as well. Okay. If you've taken physics, you can go back and recall that 1 Newton is essentially the force applied by 100 grams of a substance. If I have a kilogram, and I take that 1 kilogram, and I take that mass and I multiply it by g, which in physics is 9.8, but if we made it approximately 10 for nice and easy, then this is 10 newtons, okay? So right here, holding up some 10 newtons here. Don't have to go to the gym tonight because I'm holding up 10 newtons. That's a little heavy for my taste. I don't like to hurt myself. So we'll imagine that this is 100 grams. It's actually 200, so it's actually twice as much as what I'm talking about. But anyway, it's still fine. We'll imagine this is 100 grams. So if this is 100 grams, 1 Newton. Oh yeah, that's better. I'm more of a 1 Newton guy. Here we go. 1 Newton. If we could take this 1 Newton, which really is nothing, and we could spread it over a square meter, make that into a square, then if I were to like lay on the desk and have that land on my back, that would be 1 Pascal. Think about that. That doesn't weigh much, right? Spread that over really thin, 1 meter, and then put my finger underneath it, nothing, right? Bill Cosby used to have a stand-up comedian. A piece of paper. He's like a piece, anyway, it doesn't matter. Nothing. Next to nothing. That's a Pascal. Pascal is a phenomenally tiny little pressure unit, all right? Now, if I were to take this area and make it really small, then the pressure changes. Because if I make the area tiny, if I make the bottom of this equation small, what automatically happens to my answer? What do we call that relationship when you look at the bottom of it and you've got that number there? What do we call that relationship? When you're looking at the bottom of an equation. What do we call that relationship? Yep. It's an inverse. So what happens if I make that bottom number really tiny? The answer gets big. If you were to take this Newton and put it on a thumbtack and then put that thumbtack on my finger and me attempt to lift it, that's going to apply a little more pressure because now all of this force is being squeezed into a tiny area. And so if I make the area small, then I'm going to increase the pressure. It might even break through my skin, my tender little skin. Could hurt me. And that's because we've increased the pressure. You can see this with shoes, right? Guys, you might have, well, you guys are in prom next year. Okay, next year, guys, when you go to the prom, you take a look at the ladies' shoes, right? Especially if you're going to take them off in some part of the evening. Because if the ladies have these heels that go down to next to nothing, right? If somebody steps on your toe with a regular shoe, somebody steps on your toe, you go, oh, sorry, no big deal. That's okay. I'm all right, right? Because a regular shoe has a big area, right? And that big area means low pressure. You can even have a real big guy like myself step on your toe. Ooh, I'm sorry. That's okay. But then you could even have a small girl who's got a heel like that, and if they go, they could break bones in your feet. And that's because the area is phenomenally small, and they can generate vast amounts of pressure. So be very careful. Like I said, when you pick them up and say, "Oh, you look beautiful. Oh man, those shoes. I'm going to be in trouble. Got to be on my best behavior." The opposite effect can be seen with, let me give an example of where we've decreased the pressure. Tires, right? This is a farming community. I grew up on a farm. And you've seen tractors, I'm sure, with little skinny tires. They usually have little skinny tires so they can spray and they can get in the rows. And that's great for getting into rows, but if it's really muddy, those tires wouldn't be very good because the skinny tires would squeeze into the ground very easily. And that's because they'll apply a high pressure to a very small area. I know sometimes if there's a combine and it's really a muddy fall, they'll put these great big wide tires, right? They're sometimes called rice tires because they're designed for rice fields and rice paddies where there's lots of water. And so by spreading that area, that force of the combine or the tractor on a large area, you decrease the pressure and it doesn't cut into the field the same way. So a big area means low pressure, but a small area would result in high pressure for the same force, okay? Now that's just the physical meaning of pressure. I haven't talked anything about gases yet. That's just pressure. It's how much force is being spread over a particular area. Let's now talk about how gas pressure is affected. So don't worry about the thumbtack. That just kind of goes with my writing. No big deal. Let's talk about now the pressure of a gas. And I'm just going to bring the whole thing up, okay? And I am going to, in terms of this picture, this is just a bunch of particles moving around. If you're drawing the picture in your notes, just draw a rectangle, put your gas particles in it, and put some arrows showing the fact that they're moving kind of chaotically. And I do want one or two particular arrows showing the particles bouncing off of the walls of the container. So when you're drawing a little picture to represent it, some particles in there, have them moving around, and have a couple of those particles bouncing off the walls of the container, because that's what pressure is all about. It's all about the particles striking the walls. As particles move around in a gas, they travel in a straight line until they either run into a wall or they run into another gas particle. If they run into a wall and they bounce off that wall, they will apply a force to the wall. They have a very tiny area, and that force will impart a pressure on the surface of the wall. Now that's for one particle. But in a gas, there are billions and billions and billions and billions of particles. So how then does a gas result in, and I'm looking for a balloon, I don't think I have one. I'll grab one a little later on. Let me just finish off. I've got 3 more minutes and I'm gonna explain one last thing. So then how does a balloon then maintain its shape and its pressure? I think I can find a balloon here. I got a tiny little balloon. So how does then, tiniest little balloon ever, how does then a balloon maintain that shape due to the particles in there? Well, it's because the particles are bouncing off the balloon and they're maintaining that shape. let me bring you through one more little imaginary experiment. Imagine that you could take a grocery bag, plastic grocery bag, and in your house there is one of these dopey flies. You know the dopey flies I'm talking about? If you live in an old house, you know what dopey flies are. They come out in the spring and they bounce off the ceiling. You never see that before? They're stupid. Trying to go to sleep, they're bouncing off the ceiling, driving you crazy. All right, if you know what dopey flies are, you know what I'm talking about. So let's imagine you could catch one of those dopey flies and stick it into the bag and kind of hold the bag shut. What would you see? What would you see if you had a dopey fly in a bag? It would freak out, but what would you see on the outside? You'd see it go, because it would hit the side and then it would hit the side again. Every time the dopey fly hits the side of the bag, it exerts a little bit of pressure. Now let's imagine you could catch more dopey flies, 30 of them, put them in the bag. What's the bag now going to start to do? Move. It's going to push out, push out, push out, push out. Let's say that you then, if the flies were very small, and you could fill it with thousands of dopey flies, what would the bag look like? It wouldn't float. What would it look like? It would be pushed out. Why? There's flies striking the surface constantly, and the bag is not able to get back to its original kind of, empty shape. So because there's so many flies in there striking the surface of the bag would push out. When you blow into a balloon, you're filling it with a bunch of dopey flies. And these particles are constantly bouncing around in there, but at any point in time, there are gas particles striking pretty well every surface of this balloon. And therefore, it's pushed out because there are these dopey flies running into the wall of it. Again, if we could get into our magic school bus and zoom in to the surface of this balloon, we again would see some dopey fly action. You'd see the balloon would actually stick out and bulge every time a particle struck it. But because we're big and the particles are small, we can't see that. But that's what causes pressure in a gas. All these little particles striking the walls over and over again. All right. You're right, I do. We'll see you tomorrow.